All right, so we've been talking about flow in pipes and in pipe junctions and pipes in parallel and pipes in series. In reality, water distribution systems are going to be connected in a whole complex network that is going to include some that are connected in series, some that are in parallel, and then there's going to be junctions. So we need a systematic approach that we can use to analyze that, to deal with the complexities of real-world water distribution systems. And so if we're given the supply of water at a location and then the demands at different points in the system, it's possible to determine the flows in all the pipes and the heads in each of the junctions when you have a complex network. To do so requires the solution of a simultaneous system of equations, and those equations are going to be based on conservation of mass at junctions, which we've already talked about, and conservation of energy around loops. Okay, so if we're looking at a junction, we have lots of pipes connected together. At every junction, we know that the flow in is equal to the flow out from conservation of mass. If we look at a loop, so let's say that we've got a bunch of pipes connected together, and you can look at this junction, which here we'd have flow in as flow out. Same thing would be true here. If we look at this junction, there's two different ways that water could get there if it's flowing along these two paths, and we know that the head loss has to be the same. HL1 is equal to HL2. If you move this over to the other side of the equation, we can kind of think of this as the head loss all the way around the junction should sum up to 0 if we account for the direction here being kind of negative along this path. So if we consider this to be the positive direction going clockwise, these are positive flows and these are negative. Okay, and so these are the two key ideas, and we can use these to set up a system of equations for a network. Okay, so here's an example of a network where we have a lot of different junctions and a lot of different loops. So we've got flow coming in at two places and then going out at a different one. And so at every junction we can write a mass balance, and then for every loop we can write an energy balance. And this will generate a system of equations that we can solve to get the flows. Okay, so in this one there are 10 individual pipes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so there's 5 here around this loop, and then 6, 7, 8, 9, 10. 10 different pipes, so each of those is going to have a flow that's unknown at the beginning. And then if you look at the junctions, we've got 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 8 junctions, and we've got 10 different flows, and then we've got 3 different loops, as you can see drawn here. So that means that we have unknown flows in each of these different pipes, and across each of those distances, like from A to B, there's an unknown flow. There's also going to be an unknown loss of head. Okay, so the head loss in each pipe, if we call that delta H, can be computed with the Darcy-Weisbach equation, which we've already talked about, how you can write this as delta H is equal to K times Q squared, and then K is 8FL over pi squared G d to the 5th. And we know that F is really a variable that's going to change as Q changes, but it's not going to change a whole lot, so we can kind of pretend like it's a constant, and then we can go back and do a correction like we did with the junction example before. Okay, yeah, and that's what I've kind of written here for you. So, and then around a loop, we know that the sum of the head losses around the loop should be 0 if we account for the direction, and that's equal to K times Q squared for each of those different parts around the loop. Okay, all right, so once we've analyzed the flows around the loop, we can write a system of equations that we can solve. But when you start getting into really large systems of equations that are nonlinear like this, we need an approach that we can use to systematically find them. It becomes difficult to just guess the right values like we can if there's just one unknown, like what we're looking at the junction. We could just pick a value for that and then follow it through, and then we could get to a solution pretty quickly. When you get into these really large systems, it's not practical. And so there's a technique that is widely used called the Hardy-Cross method. And Hardy-Cross was actually a structural engineer. He was an engineering professor at UIUC. But he also recognized that the analysis that he had done for structures could also be used in pipe networks for hydraulics. And the idea is to use the method of moment distributions that he developed to balance the flows across a pipe network the same way that it is done for balancing moments on a structure. The basic idea is to apply a blank to the nonlinear relationship between flow rate and head loss. So if you have a bunch of linear equations and unknowns, you can solve those with matrix algebra. Even if they're very large matrices, it's not that difficult. It is much harder when they're nonlinear. So one way to make a nonlinear problem not as difficult is to make it linear. So we're going to use a linear approximation to the nonlinear relationship between flow rate and head loss in order to come up with something we can solve. So let's think a little bit about this idea of a linear approximation. So just as a reminder, hopefully something that you learned in your algebra calculus classes, I guess, calculus. So in the figure here below, what is the formula for the linear interpolation of this function f of x? We're not told the equation, we're just given this curve, and then at x equals 2, we want to write a linear approximation. So we can see that it's nonlinear because it's curving. If it was linear, it would be straight. If we look at this point, then the linear approximation would look like what? What would that be? Remember that it's the tangent to the curve there, the straight line, okay. So this is the linear approximation. And what we really want here is to come up with an equation, okay, to describe this line. And so remember, the way that we can do that is if it's a line, we need to know the slope of the line, and then we need to know how high up and down the line is with something like the y-intercept in order to be able to solve this. Okay, so to get the slope, we need to take the derivative. So we need f prime of x. And so if we look here at x equals 2, f prime, which is df dx, the slope is equal to the change in y over the change in x. And so you can see here that it goes pretty much through this point at 6, and then through this point at 10. And so this is going to be 10 minus 6, and then the change in x here is 3 minus 2. So that means we get a slope of about 4 for this line. So that's going to be our approximate derivative. And then the formula here for our linear approximation at this point is going to be f of x is, it's not exactly, but approximately equal to f of x at x equals 2, the value at this point, and then if we go linearly away from there, it's going to be plus f prime of x at x equals 2 times the change in x. Okay, so this is the starting point plus the slope, which is rise over run, times the change in x. Delta x times the slope tells you the change in y. And so, if you start going all the way out here, you can see we would slightly underestimate f of x because our linear approximation isn't right. But this is the general formula. And if you're close to this point, it's reasonable. Okay, and so remember, the reason that we're doing this is we need to come up with the linear equation so that we can work with it to solve these problems. Okay, and so in this example here, f of x is going to be approximately equal to f of x at x equals 2 is 6, and then f prime at x equals 2 is 4, and then delta x, okay, which would be this is x is equal to 2, and so it's just going to be like x minus 2, whatever the actual value is. Okay, so this is going to be our linear approximation. So let's think now a little bit about how this can be applied to hydraulics problems. So for a given set of flows, the head loss in each pipe can be determined So once you know what the flow is, we know the equation to relate flow with head loss, and then we can go through and adjust the flows to reduce the errors. That's the idea. So the magnitude of the adjustment that we need can be determined using the linear approximation of the quadratic function that we are working with here. So the linear approximation for a function f is f of x at x0 plus delta x is equal to, again, the starting point. So if I make a small change, delta x, it's equal to the starting point plus the derivative at that point times that small change in x, okay? So the starting point plus the slope times the change in x is approximately equal to the value if I go slightly up or slightly down from that point. And so by linearizing flows, we can come up with a pretty good estimate of the adjustments that we need to close off the errors across a given loop. Okay, so across a loop, remember, we have to have an energy balance, and if we make a guess at what all the Q's are, then we need to go and update those in order to make the energy balance work, and it's going to be a lot easier to do that if we use this linear approximation. Okay, so this is what it looks like for a function f. Now let's think about what it looks like for the real function we're working with here in these hydraulic problems. And so delta H at Q0 plus delta Q, okay, so we instead of F we have delta H, instead of X0 we have Q0, instead of delta X we have delta Q, okay? And so this would then have to be, okay, instead of F here we get just delta H, and instead of X0 we get Q0, right? And then here we have plus, instead of F prime of X, we're going to get delta H prime. And instead of X0, we get Q0. And then instead of delta X, we get delta Q. Okay? So all I did here was switch F for delta H, X0 for Q0, and delta X. Okay? And then remember, we have our formula here for delta H, which is equal to K times Q squared. Okay, so we can come up with this approximation. And so if we go around the loop, the sum of the head losses should equal to 0, and we can apply our formula here for the approximate value of Q0 of delta H, sorry, given Q0, and write this for each of the equations. And then we can use this expression to figure out what the value of delta Q needs to be, how much they each need to be adjusted across a loop in order to make the energy balance still work out. Okay, so if you solve this equation here for delta Q, then you end up with, move this over and you get a negative sign and divide, we come up with this. This is going to be our estimate for the change in the Q's around the loop in order to get that to work out. Okay, and yeah, so remember delta H at Q0, so we have, just to show you where this equation comes from here, delta H is K times Q 0 squared, or delta H times Q squared, and so delta H at Q0 is just K times Q0 squared, and then the derivative of KQ squared, okay, that's not Q0, is the derivative of this with respect to Q is 2 times K times Q, so that's where this comes from, 2 times K times Q, and if we put in the value of Q0 there for Q, we get that, and then times delta Q. Okay, so this is our approximate formula here for the value, and then once we solve that, we end up with this relationship here. Okay, so this gives us, so basically the procedure that we're going to use to solve these problems is we're going to go in and make an initial guess for all the flows in a network, and then we're going to go around each of these loops, and we're going to make an adjustment to make the energy balance work over and over again until all the adjustments are negligible, and then we'll know that we're at the end. All right, so I'll do an example where I show how you work through this next.